Again, welcome to Mathematical Structure for Computer Science, CS113, also known as Discrete Mathematics at Pace University. In these lectures, we're going to cover Chapter 11 of our course textbook, Trees. And our main objective of these lectures is to go through what is a spanning trees, what is a depth first search, also the breadth first search, and depth first search in directed graphs also. So first we start with the definition of a spanning trees. And here we say, let G be a simple graph. A spanning tree of G is a subgraph of G that is a tree containing every vertex of G. So again, G is a simple graph and a spanning tree of G is a subgraph of G that is a tree containing every vertex of G. So for example, we have a graph here and they say we should find the spanning tree of this simple graph. So first we look at the graph and we can see that we have A, B, C, D, E, F, and G vertices. And we can see that the graph is connected. All the vertices from A to G are connected. But it's not a tree. This is not a tree. The reason why, it contains a simple circuit. As we can see, a simple circuit A, B, E, and F. A simple circuit is when we start in one vertex, we can end at that vertex. It's kind of like having a loop. So this means the graph is connected. First, we can see A, B, C, up to G. All the vertices are connected. But it's not a tree. So I'll go back to the definition again. We say we have a graph, G, which is a simple graph. The spanning tree of the graph is a subgraph of G. That is a tree containing every vertex of G. One of the main principles of a tree is that we start from the root and we don't go back again. So we start from the root and we go down to the next level of the trees with vertices, and we visit all the vertices from up down. We don't go back to the same vertex again. When we go back to the same vertex, then it's a graph. And so what we have here, and we say it's a tree, it's actually a graph. Why? Because we have, again, a simple circuit. Example is AB, A, B, E, F, A. So our solution here is convert the graph to a spanning tree, which means our first goal is to remove, or we have to get rid of all the simple circuits. Again, this is a graph, but it's not a tree. And the graph is connected because we have all the edges connected to each other. The reason why it's not a tree, because again, it's a simple circuit. It contains a simple circuit. So the first thing we can do is to remove possible edges. Now, our definition for a spanning tree means we are going to maintain, or we are going to have all the vertices from A to G, but it will no more be a graph, but rather a spanning tree. So the goal is to remove as much edges as we can so that we can remove all the possible simple circuits. So for example, we are going to remove the, when we look at the graph again down, we can see that we remove the edge AE. And that again helps us to get rid of a circuit, a simple circuit, which will be the A, B, F, E, A. Now we end at E. We can't go back to A no more. So this is now, simple circuit is gone. And so here we say now one simple circuit is gone, but there's a remaining subgraph still have some simple circuit. We can see C, G, F, and C again. still a simple circuit. So the first thing we can decide is to remove E and F edge. So remove E and H because we can also get a simple circuit here by going E, G, F, and back to E again. So remove E and F. So this means now we have two simple circuits are removed. And also, if we like, we can also remove C and G because we can see that we have F, C, G, and back to F again. So that's a simple circuit. So we decided again to remove C and G. And this will be our final graph. And when we look at this graph now, we can see that there is no simple circuit. Any edge is connected. We have a, for example, if I'm in a vertex A, I can't come back to A no more. If I'm in B and I go to A, I can't go around to come back to B. Same thing applies to E, F, G, C, D. So now this is the definition of a spanning tree. So a spanning tree is when we have a graph and the graph is connected, but it consists of simple circuits. If we can remove all the simple circuit from the graph and maintain the same number of vertices, then it becomes a spanning tree. So here we say the graph is connected, but this is not a tree because it contains a simple circuit. Again, the edge, it doesn't matter. You can remove AE first, or I can remove CG first, or I can remove EF, etc. I will not remove E to G because you can see there's no any edge between. I mean, there's no any vertex between E and G. We always remove, well, for example, we remove AE because we have AEF. Then B, then come back to A again. We remove EF because we have EGF, then back to E again. We remove CG because we can go G, E, F, C, and back to G again. So our goal of a spanning tree, the whole concept is that the graph is given, the graph is connected, and it has a simple circuit. If we can remove all the simple circuits and maintain the same vertices, it becomes a spanning tree. So there are so many ways. Here we have two major algorithms that we can use to build a spanning tree. We will go through the depth first search and also breadth first search. These two algorithms are used a lot in the artificial intelligence class for searching algorithms, gaming concepts, etc. So to use depth first search to build a spanning tree for a connected simple graph, first arbitrary, we should choose a vertex of the graph as the root. So first we need to, the algorithm said the first thing we need to do, we are using the depth first search to build a spanning tree. First, we need to choose any of the vertex as our root. Now, after we get our root, we will form a path starting at this vertex, that's the root vertex, by successfully adding vertices and edges where each new edge is incident with the last vertex in the path, and also a vertex not already in the path. We continue adding the vertices and the edges to this path as long as possible. Now, if the path goes through all the vertices of the graph, the tree consists of this path is a spanning tree. Otherwise, the concept of backtracking, we move back to the last vertex in the path, and if possible, we form a new path again, starting at this vertex and passing through the vertices not already visited. If this cannot be done, move back another vertex in the path. We'll repeat this procedure until we visit all the vertices in the graph and we form a spanning tree. Again, the algorithm here, what it means is that we choose one route. Then when we choose one route, we will visit the next vertex. Then we form an edge with that vertex. Then we move to the other next vertex. If there's a possible path, we keep going. Now, if there's no path no more, we have to backtrack. We have to go back. And if we didn't visit any vertex, then we move to that direction and form a new path. If there's none, we go back again until we go through all the vertices in the graph. I think the best way to explain this is by doing an example. So this is a very good example for it. So here you can see that we have, again, a graph, and we want to form a spanning tree. So the question says, use the depth first search to find a spanning tree of this graph. So what the algorithm says is that take any of the vertex as the root. Then we go through all the path. Let's say I take F, and I'll go through the path to G, and then K, and then J. I can't go no more. So now I have to come back. So I'll come back to K. There's no any vertex that I didn't visit. And I'll come back to H. Oh yes, I didn't go I, so I'll form a new path here. I'll go through I. Now when I go through I, there's no other vertex to visit again. So I'll come back again, then come back to F. When I started F, I went to H. I didn't go K, so I'll go K this time. Then I'll form the edge there. Then I'll come back again because after H and G, I can't go no more. So I'll come back, then I'll go through E and form a new path and so on. So let's see how we solve this problem. So here we say we start first arbitrarily with vertex F. So we are using vertex F as our root. So I have F here, so I put F. From F, you see, I said I'm going to H, then K, then J. Here we decided, okay, we build a path by successful harding an edge that connect the last vertex added to the path, and then a vertex not already in the path, as long as this is possible. So the result is a path that connects. So we went through F, then we went through G, then we went through H, then we went through K, then we went through J. So F, G, H, K, and J. So this is what we form. Then after when we reach J, there's no more, we can't go no more further. So next we return to K. So we return to K. But when we return to K, we find that there's no any new vertices to add in K. So what we do, we return to H. When we return to H, we find out that we didn't go I. So I'm going to go I. So that's where we have I here. So you can see that I connect I with H. If, for example, there's a vertex in K that I visit a new vertex, then I'll connect that with K. So I'll connect it with, again, I. Now, when I reach I here, there's nothing I can go further. So I'll return back to H. And I already went through F and I already went through G. So I'll come back. And when we look here right now, we can see that again, we have formed F, G, H, K, J, and I. So I. So we go back and we return to H. There's no any new. And then we move to F. And when we reach F, we had a new path F to D, because F, we already went through G. So we start with G, H, K, I, K, J, then came back to K. There's no any new vertex. We came to H. There's a new vertex I. We went there. We can't go no more. So we come back to H. There's no more new vertex when we are at H. So we go through F. F, we have a new vertex. We didn't go through D. So now we can go through D, we can go through E, we can go through C, and we can go through A. Another person may say, okay, I'll go through C, then I'll go through B. It's the same. Here, actually, that's why we use the term habitually. We can select any route, any of the vertices as our route starting. The only thing, we're going to have a spanning tree, but the paths may be different. And is correct. So here, we decided to go through A. After that, we can't go no more. So when we connect it, remember we were in F before we were able to go through D, E, C, and A. So you can see that in F, we have the D, E, C, and A. So if we can't go through no more, we come back to C. But when we came back to C, we saw that we didn't go B. There's a new one. So you can see that a C at a C, we were able to connect A and B. So at C, we have also B. So this will be our final graph. Now, spanning graph. Spanning tree, sorry. It's a spanning tree. So you can see that from the graph, we were able to form our spanning tree. Our root is F because that's where we start from. Another example would be I may start from the root of H. You will get the same spanning tree. The difference is the path may be different, but it's a spanning tree. So that's our definition again. And I can go back one more time. We see our definition. So we said a spanning tree is if we have a graph, G be a simple graph. A spanning tree of the graph is a subgraph of G that is a tree containing every vertex of G. That's it. And we know the definition of a tree means we need to have a root and we cannot visit the same vertex twice, which means we can go down and come back up again. So again, that's the solution here for the first search algorithm. And also the theory is given to use the first search to build a spanning tree for a connected simple graph. First, arbitrarily choose a vertex of the graph as a root. Then from there, we move on, we form the path. So the edges selected by the first search of a graph are called the tree edges. And also all other edges of the graph must connect a vertex to an ancestor or the descendant of the vertex in the graph. These are called the back edges. And also in this figure, the tree edges are shown with the heavy blue lines, and also the two thin black edges are called the back edges. Because we say all other edges of the graph must connect a vertex to an ancestor or descendants of the vertex in the graph. These are called again the back edges, the black. So we now see the pseudocode to specify the first search. In this recursive algorithm, after adding an edge connecting a vertex V to the vertex W, we finish exploring W before we return to W to continue exploring from V. So this is the pseudocode for the algorithm for depth first search. Graph G is connected graph with vertex V1, V2 up to Vn. A tree will consist of only of the vertex V1. So we visit V1, then recursively V, we visit the vertex of G. Now for each vertex W adjacent to V and not yet in the T, we had a vertex W and the edges VW to T. Then we recursively again visit W. So next will be the breadth first search. Same thing, we can also construct a spanning tree using the breadth first search. We first again arbitrarily choose a root from the vertices of the graph. But this time, we are going to add all of the edges incident to this vertex and the other endpoint of each of these edges. Then we say that these are the vertices at level 1. So there's a difference here. After we select our root, we had all of the edges incident to the root vertex that we selected and the other endpoint of each of these edges. Then that will be level 2. Now for each vertex added at the previous level, we are going to add each edge incident to this vertex as long as it does not produce a simple circuit. So the goal again is to get rid of the simple circuit. We know the definition for spanning tree is when we have a graph and we remove all the simple circuit and we still keep all the vertices. So we're going to continue this manner until all the vertices have been added and we have a spanning tree. So best way again, let's see an example. Here they say now we should use the breadth first search to find a spanning tree for this graph. So we again arbitrarily choose a vertex as a root, and this time we choose E as a root. Again, there is no theory or any method to follow to choose your root. You can choose any vertex as the root. Here we chose E. So if E is our root, which we have it here, we then add all the edges from E to BD. So we have to look at E. So when we look at E, E have incidence vertex or connect to F. E also connect to B. E also connect to D. E also connect to I. So we use the E as our root and we connect to all these 4. And that will be our level 1. So you can see here we have a B, D, F, and I. We don't have A because A is not connected to A. There's no any edge between E and A. So that will be our level 1. So here we say we arbitrarily choose the vertex E as our root. We then add the edges from E to B, D, F, and G. These 4 vertices make up level 1 in the tree. Next, we add the edges from B. So right now, this is our level 1. So we know we have to connect. I'll start from my leftmost. I'll look at B. But B, we are adding to A and C, which means there's an edge between B and A. There's an edge between B and C. So let's look at the graph. This is our B. We can see that B, we have edge between B and C and B and A. We cannot add B and E because we already have EB. E is our root. So we can't go back there anymore. So that's why we have this form B, we have A and C. The same thing applies to the next. We use the B, we can now use the D. We took B already, now we are taking D. So because we already, when we're at E, we form B, D, E, F. So now we are going through B, D, E, F. So B, we get A and C. With D, we get A and H. So with remember we already have A because we have B. B is A and C. So if I'm at D, I can't use A no more. So I can use H. So when you look at the graph here, we have H. Then we go to F. F we can't use E, it's our root. We can't use C because we use C already for B, C. We haven't used J, so we can use J. We also haven't used H. So F, we have J and H. So when we look, F is J and H. F is J and H. Then the last one is I. So I'll go through I. I can't go to E. We cannot. E is our root. And I can't go to J because F and J is already. But I can go to K. So when we look I, we have K. I cannot go I and H because I already did D to H. So which means I will have only K. So here we finish the second level because our root, we have the 4 connections. This is our level 1. Then the level 1 will look all their children and we're able to finish. So we have our level 2 completed. Now we go to level 3. Now level 3, we can start from A again. We know A, we finish everything here. A, B, everything is done. So there will be nothing in A. C also, there will be nothing. We did B and F. And also H. H, we are here at H. We already did K. I went with K. And we did D already. So we don't have anything here. Now we go to G. G, we have L because L connects to only G. We haven't visited there. So we have G and L. Then J. In J, we already went through G now. We went through F, we went through I. So we don't have anything for J. Then we went through K. K, I, and H is already gone through with K. But M by itself, so we go through M. And that will be the span, our final spanning tree. So we can see the difference between depth first search and breadth first search. Breadth first search said take any root. Then the next level of the tree, which is the first level, it will be the root with the vertices that are connected to it. And that will be our level 1. Then we have to look at those vertices at level 1 to see which vertices are connected, which we haven't visited before, we haven't used before. So we have BDEF, we went through B, there was AC, we went through D, there was only H, we went to F, we have G and J. F, we have G, and then we have J. We couldn't go E or C because we went through E is our root and we went through C already. B with C. So if any vertex connect, let's say B connected with C, I can't use F and C no more. If I is connected to J, I cannot use H and G or E and I. I mean, I can't use H and I or E and I no more. So that will be our final, again, result. Now, if I'm doing depth first search, the concept is that I'll take the same E again. Now, when I take E, I decided to form a path by going through I, J, F, H, and L. So I formed the path there, which I will include in my tree, that path. Then when I reach here, there's nothing. So I'll come back to G. G, there's no any new vertex. And I'll come back to J. We have a new vertex here, which is I. F, we already did that, so only I. So I'll go at the J node and form a path with I and J down. And from here, I can go forward from J still. I can go, F was our root, so I can go through E, I can go through B, I can go through C. Or if I didn't go C yet. If I go through C already, then go through A. So that's how the concept of depth first works. But breadth first says, take any of the, let's say I take F as my root, then all the edges connected to F, I have C, I have G, I have J, I have E. So that will be my first level vertices connect. Then I will look at that to do the rest. I may start with E. If I'm in A, I didn't go B yet, I didn't go I yet, I didn't go D, so that can be the children. And we keep going. So this is the algorithm for breadth first search. We say the procedure for breadth first search. We have our graph G, which is connected with vectors from V1. So we have our algorithm for breadth first search. We have T is our tree, consists of only of the vectors V1. L is our empty list. So we visit V1 first. So now they say put V1 in the list L of unprocessed vertices. So unprocessed vertices means the vertices that we haven't visited yet. Then why L is not empty? If L is empty, then we finish. Even if it's only one node, then V, then we finish V1. If it's not empty, then we'll remove the first vertex V from the L, which means we don't want to visit it again, so we'll remove it. Now from each neighbor of W, let's say the W is the vertex, vertices that are connected to W that we have not visit, we are going to add them. So if W is not in L and not in T, then add W to the end of the list and add W and edge VW to T. We also have the depth first search in directed graphs. So both depth first search and breadth first search can be used easily, modified to run on a directed graph. But the result is not necessarily a spanning tree, but rather a spanning forest. So example is given here. For the graph in A, if we begin at vertex A, depth first search has the path A, B, C, and G. So we use the A, B, C, and G. At G, we are blocked here. That is, we can see this is a directed graph. So remember, we go by the direction. So that's why we couldn't say A, B, C, D, because D is what going towards C. So we can get A, if we use A as our root, we get A, B, A to B to C, but we can't go C to D because D to C rather. So we go from C, we were able to go up to G. So G, we are blocked, we can't go no more. So that will be the end. So we are going to have the path A, B, C, and G. Then at G, since we are blocked, we can return back to C, return to C. Next, we are going to have the path connect F to E. Because when we come back to C, we go back to B, then we have F here. So we had it to next, we return to A and find that we cannot also add a new path. So we begin another tree with D as its root. Then we find that this new tree consists of a path connecting the vertices D, H, I, K, L. We have D, H, I, K, L. Again, we have to pay attention to the directions. So we return to A. When we return to A, we find that we cannot add a new path. When I'm A, E, and B. Then we find that this new tree consists of a path connecting the vertices D. From D, I can move to H. When I'm at H, I can move to L. When I'm at L, I can move to K. When I'm at K, I can move to J. But after I reach J, I cannot go to I. And we already went F. So finally, we had a new tree which only contains I, its root. So this is the answer we get. To index websites, Search engines such as Google systematically explore the web starting at no point site. Then the programs that do this exploration are known as the web spiders, or sometimes we use the term the crawlers. The idea here is how there's algorithm that we use, which make it possible for Google search engine. We start from one web page to the next and move from the next to the other, etc. And the algorithm is called again the web spiders. So to index websites indexes, we need to visit all the websites. So search engines such as Google systematically explore the web starting at the known site. The program that do this as exploration also is known as web spiders. So we have some few questions here. Problem one said we should find the spanning tree of a graph below by removing edges in a simple circuit. So here is a graph and we have a simple circuit A, B, D, and back to A again, or B, C, E, and back to B again. Remember, to find a spanning tree, we need to keep all the vertices and remove the simple circuits. So since the edge AB is part of the simple circuit, we can remove it. Or I may decide to remove AD. So it depends. We remove AB, then since edge BC also is part of simple circuit, we can remove it. At this point, there are no more simple circuits. Then we have a spanning tree. Because here we have two simple circuits, A, B, D, and B, C, E. So I just have to remove one edges. So decided to remove AB, and next we decided to remove BC. And that's the solution. So we're going to have a spanning tree with AD, BE, and C. When we are at C, we can't go back to B no more, since we went from B to E. Another question, they say we should find the spanning tree of the graph below by removing edges in a simple circuit. So the same thing here, we have a lot of simple circuits here. AHI, BIJ, CJD back to C. So all these are simple circuits. So here we say we can remove these edges to produce a spanning tree. The edges we can remove will be AI, then BI, then BJ. We can also remove CD. So it's like we remove one of this. And the same thing apply here. We can remove JI, FJ. And so we have removed the FJ, we remove JI, we also remove FI. FI down here. Then remove EI also, EI. Remove EJ. EJ. This is I, this is J, EJ. And then we form a spanning tree. So you can see that we still have all our vertices. The only thing we remove A, I, B, I also, then BJ, then CD. So we leave CJ, remove CJ, then remove CD. Then we also can remove EJ and FI, and also FJ, and also GI. And the rest we have a spanning tree with no simple circuits. Now, next question says, draw all the spanning trees of a given simple graphs. So we have a very simple graph here, A, B, C, and we come back to A again. So that's a simple graph with a simple circuit. The circuit is A, B, C, back to A. So to draw the spanning tree of this, I may remove the AB. So I may have ACB. Or I may remove AC and I may have ABC. Or I may remove one of the BC down and I may have ABC. these three options, they are all spanning tree because where I start, I can't end it at the same place. Now, in the next exercise, which is question 14 of our course textbook, they say we should use the depth first search to produce a spanning tree for a given simple graph. And here they told us to choose A as the root of the spanning tree. So this is very important because the route that we choose will give us a different spanning tree. The path will be different. So that's why this question is telling us to choose A. So if I choose A here, remember this is a depth first search, which means I can go through A, B, C, H, I, D, E, F, K, J, N. I don't want to come back to I already because I went through I. So that's where we are going to end. So again, let's go through the step. So the tree is shown in heavy lines. So we can see the heavy lines. That's our tree now. It produced by starting at A, because the question says we should choose A as our root. So by starting at A and continue as far as possible without backtracking. So I can go A, B, C, H, I, D, E, F, K, J. So that's the highest I can go. Then we're going to choose the first unused vertex in alphabetical order at each point. When the path reaches the vertex L, we need to backtrack to H. We can then form a path all the way to N without further backtracking. Finally, we backtrack to vertex I to pick up vertex M. So that's the solution. So this will be the conclusion of our lectures on spanning trees, which cover chapter 11-4, section 4. So again, wish you the best. If you have any question, send an email or you can reach me at my contact number. This material will surely be in the final exams. So again, wish everybody the best. Thank you.